As we know that the electrical network is said to be solved when all the voltage and all the currents in its different elements are determined. So there are two general approach to solve a electrical networks. These are direct method, another one is network reduction method. Okay, now what is the direct method? Direct method is if the circuit is simple, then the network is left in its original form for determining the voltages and currents. So this method is known as direct method. For example, Kirchhoff's law, Maxwell loop current method, nodal analysis, superposition theorem, etc. Now what is network reduction method? If the circuit is complicated, then the original network is converted into a simplest equivalent form. Okay, so for determining the voltage and current, such a method is known as network reduction method. For example, Thevenin's theorem, Norton's theorem, delta star conversion or star delta conversion, etc. So today we will discuss about direct method, and from this direct method today we will discuss about Kirchhoff's law. Okay, now Kirchhoff's law, these laws are more comprehensive than the Ohm's law, okay, and are used for solving electrical networks. These theorems are particularly useful in determining the equivalent resistance of complicated network of conductors. Another for calculating the currents flowing in various conductors. Okay, so again there are two laws: Kirchhoff's current law, KCL, another one is Kirchhoff's voltage law. Now first we will discuss about Kirchhoff's current law. So it states that there in any electrical network, the algebraic sum of currents meeting at a point or a junction is 0. Suppose we'll consider a point A. Here I1, I2 and I3, these are incoming currents, and I4, I5, these are outgoing currents. So as per KCL, sum of all currents equal to 0. The algebraic sum of current is 0. So I1 plus I2 plus I3 plus of minus I4 plus of minus I5 equal to 0. Therefore I1 plus I2 plus I3 equal to I4 plus I5. So sum of all the incoming currents equal to outgoing currents. Now Kirchhoff's voltage law. So it states that the algebraic sum of the products of currents and resistance in each of the conductors in any closed path or a mesh in a network plus the algebraic sum of the EMFs in that path is 0. That is, sum of IR drop plus sum of EMF, this is equal to 0 in a mesh, okay, or a closed path. This is KVL. Now the determination of voltage sign, because as we know that as per KVL equation, sum of IR drop plus sum of EMF equal to 0. The algebraic sum of this two drops, IR drop and EMF equal to 0. Now we will determine the voltage sign. Voltage sign for two parameters. One is sign of battery EMF, another sign of IR drop. Okay. So first we will discuss about sign of battery EMF. So for this so sign of battery EMF, suppose a rise in voltage should be given positive and fall in voltage should be negative. Okay, so keeping this in mind, so suppose this from this figure, point A and point B, suppose sign of when we go from positive negative terminal to positive terminal, okay, from negative terminal to positive terminal, then there is a rise in potential. rise in voltage, that means rise in potential, then it's positive plus E. When we, for second case, when we go from positive terminal to negative terminal, then it's fall in voltage, and the voltage is minus E for this case. When you go for negative terminal to positive terminal is rise in voltage. When you go from positive terminal to negative terminal, then it's fall in voltage. Okay, in case of battery EMF. Now in case of iron drop, suppose if we go through a resistor in the same direction as current, that means motion, if you go in the same direction of current, then there is a fall in potential, then V equal to negative minus V, and IR drop is minus IR. Now however, that means the current flows from higher potential to lower potential. Now if we go in the direction opposite of current, the direction of motion is just opposite of current, then the voltage rise should be positive, and there is a rise in voltage, and voltage rise should be positive. So it's positive V, and this is positive plus IR. Okay. Now suppose a circuit, this is a circuit, simple circuit, R1, R2, R3, these are given, and this is the direction of travel, or that is direction of motion is given. So now we'll find which one is rise in fall in potential or rise in potential. Okay, so for this case, the current direction of current I1 is this way. So the direction of motion and direction of current both are in same direction. So it's a, so this condition, current and motion both are in same direction, it's a fall in voltage, that is minus, for this case, minus I1 R1. So I1 R1 is negative. Again for this case, the direction of current and direction of motion or travel both are in same direction. Again I2 R2 is negative, and I3 R3, in case of I3 R3, direction of motion and direction of current, these two are opposite direction. So if these two are in opposite direction, when current and motion, these two are in opposite direction, then it's a rise in voltage or rise in potential. So it's positive. So I3 R3 is positive. Again I4 and R4, direction of travel and current both are in same direction. So again, if both are in same direction, then it's fall in voltage, that is negative. So I4 R4 equal to negative. Okay. Now E1, in case of E1, this side is positive, negative, right? So direction of motion or travel, and E1, if, as you know that, when consider this case, sign for the sign of battery EMF. So when direction of motion from negative to positive, then it's rise in voltage. So for this case, again direction of motion this way, so it's from negative to positive, so it's rise in voltage, so it's a positive. Okay. Now for this case E2, this is positive and negative. So direction of motion from positive to negative. So as you know that, for when direction of motion in case of battery EMF is from positive to negative, then the resultant value is negative, fall in voltage, it's negative. So for this case it's negative, so E2 is negative. Now using KVL, Kirchhoff's voltage law, as you know that sum of IR drop plus sum of EMF equal to 0, algebraic sum of IR drop, algebraic sum of EMF equal to 0, right? So now we'll put all the IR drops, that is I1 R1, it's negative. Okay, I1 R1 negative, all the IR drops. I2 R2 is again negative, I3 RT3 equal to is positive, and I4 R4 is negative. Okay. Now for sum of all the EMFs, for EMF there is only two EMF batteries, E1 and E2. So as we calculated our E1 equal to positive, E1 is positive, so E1 is positive, E2 is negative, is this equal to 0. So sum of all the IR drops, algebraic sum of all the IR drops plus algebraic sum of all the EMF equal to 0. This is the as per KVL equation. So IR drops, all the IR drops equal to this. So for this circuit the KVL equation is this. Okay. So in our next video we will solve some numerical based on Kirchhoff's law. So thank you for today. Have a good day.